Hello, everyone. So I just wanted to make a short video, as short as I can, in order to go through the example of the last RCT we saw in class. So basically, I'm just going to be going over the RCT for this fake CV study. And the main idea is that I can go a little bit more carefully through the R code. So if you have any questions, you can hopefully get them resolved in this short video. Okay, so let's just start setting up the main gist of this study. So if you remember, basically what researchers wanted to study here was whether there was racial discrimination or gender discrimination in the labor force. Okay, so of course, because we can't actually randomize race or gender, what the authors did here in this study was to randomize how names sounded. Okay, so basically they had a bunch of fake CVs that they sent out to different companies that were looking for people, that were looking for applicants. And basically they randomized whether the CV had a female sounding name or a male sounding name, or if the CV, had a white sounding name or an African American sounding name. Okay, so beyond that, which we're gonna look at as the treatment, all CVs were kind of the same. Okay, they were randomized with different characteristics, but all those groups were comparable between each other. Okay, so the measure that we're going to be looking at the outcome, it's going to be whether the applicant was called back or not. So the main idea here is that if African American CVs with African American sounding names receive less callbacks than CVs that have white sounding names, that is a clear indication of racial discrimination in the workforce, given that CVs were comparable between both groups. Okay, so now let's get a little bit into the actual data so we can explore this some more. I don't have our studio here. Where's my studio? There it is. Okay, great. So now basically I'm just going to load the data. This is the code that was available for this week. Again, if you don't have the Estimate-R package, you should install it beforehand. But other than that, all these packages should be already on your library. So we're going to load this data set, which is the actual data from the study. And as you can see, we have a lot of different variables, 65 variables, a little bit under 5,000 observations. Okay, and we have a lot of different characteristics. I'm going to just focus on a few variables of interest that we're going to be looking at. Okay. So for instance, we have education, whether the education was not reported on the CV, whether this is a high school dropout or a high school graduate, whether it indicates that has some college education or not, and also whether they finished college and, for instance, a postgraduate degree. We also have the number of jobs listed on the resume, the years of experience, whether they have computer skills or not, whether the CV is a high quality CV or a low quality CV. We have those things too. And the two main treatment variables here are going to be sex, which basically is whether the CV has a female sounding name or a male sounding name, and race, which again is going to be whether the CV has a African American sounding name or a white sounding name. Okay, for this analysis, we're going to just focus on the race treatment. But again, I really encourage you to look also at the gender treatment and see whether you find similar things using that intervention. So let's assume that we're only interested in the race treatment. Okay, we first want to create a variable that is going to be 1 if the name was African American sounding, and 0 if it was a white sounding name. Okay, so I'll just give you 1 minute. If you want, pause the video here and you can try to create this new variable treat under these things. Okay, so now I'm going to show you how this actually goes. So we are going to use our function mutate. Hopefully you are already very familiar with this. This is the function that we use to create new variables. Okay, so we're going to define the variable treat in this case, and we're going to use an if-else function. Okay, in this case, if the variable race is equal to B, which again stands for black sounding name, Then I'm going to assign the treatment variable a 1 and 0 in another case. Right? So I just run this line of code, and as you can see, now I have 66 variables. Okay, I added a new variable there. One important thing that we also should check in an RCT data is basically how many units or how many observations I have in each group. So in this case, I want to count how many observations I have in my treatment group, meaning how many CVs I have with a black sounding name versus how many CVs I have with a white sounding name. This is pretty easy with a function that we're going to be using a lot, which is group by. So group by, what it basically does is collapses my data at the level of the different levels of the treatment. So in this case, treatment, or the treat variable has only 2 levels, 0 and 1. So what this is going to do is just collapse my data frame D into these 2 bins, 0 and 1, right? And then I can do a lot of things with that. For instance, get the summary statistics for the characteristics by group and things like that. But for now, I just want to do a very simple count, okay? So again, I will first collapse my data at the treatment level, 0 and 1, and then I just want to count how many observations there are in each of these different bins. So let's look at how this actually goes. And as you can see here, we have the same split for CVs on the control group and in the treatment group. So there are 24, a little bit over 2,400 CVs with a white sounding name and a little bit over 2,400 CVs with a black sounding name. Okay, so that's great. We get like a 50-50 split that actually is going to be good for statistical power. We're going to talk a little bit about that, hopefully, the next class. But usually that is something that we want to see, a 50-50 split between a treatment and control. So the first thing I also told you that you need to do when you get RCT data is actually check for balance. That is very important because this kind of gives us an idea of whether the randomization worked or not, in the sense that both groups, we would hope so, are comparable in terms of those observed characteristics. Okay, remember that a few of them could potentially have a significant difference, right, just by chance, but overall, most of the characteristics should be balanced between the treatment and the control. Okay, so that's what we're going to be focusing on. So for this, I have a lot of covariates here. So I have 66 variables. One of them is the treatment, race, and gender is the other one, and the outcome. So basically I have like 62 covariates. That's a lot of covariates, and they will really not fit in one nice table. So I'm going to subset this and only look at a specific group of covariates. Okay, you can also do this with all the covariates. That is fine. It's just going to yield a very, very big table. Okay, so when we're looking at a balance table, the most important thing that you should focus on, again, is only on covariates. We don't want to check the balance on the treatment. Sorry, not on the treatment, on the outcome, basically because that doesn't necessarily need to be balanced, especially if there's a treatment effect. Those two averages could be substantially different, okay? So we just want to look at covariates, okay? Only X's. So what we're gonna do first is just select a set of covariates that we're interested in addition to our treatment variable. Okay, so this is what we do right here. Actually, we don't need this, that is fine, unless you have loaded another package that kind of clashes with this. In this case, we have not. So we're gonna create the dbal new data frame, which basically is just gonna be a subset of our original D data frame, okay? So I'm going to select these different variables. So the treatment and all these other characteristics that I already talked about before. So let's create this new data frame. So as you can see here, we have exactly the same number of observations. We don't want to lose any observations, but we did drop a lot of the other covariates, okay? Again, we're just gonna be focusing on these 7 covariates in this case. Then, in order to get a balance table, there's a lot of different ways that you can do this, and you can, again, go online and check for different balance tables. There's a lot of packages that have different ways to create balance tables. I find that this one in particular that I'm going to show you here is one of the most clean ones, especially if you want to like put it in a write-up or things like that. The output is super clean, and it also gives us a lot of the information that we want, okay? because what you would want to see on a data table is both the average for the treatment group and the control group for the different covariates. And also you want to see whether the difference between both is significant or not. I mean, statistically significant or not. Okay. And this is something that this function actually shows us. So this is what we're going to be using. So the function that I'm talking about is called data summary table, and basically is part of the model summary package that I made you load up here. Okay. So if you want to get more information about this, you can actually get the help file, and it's pretty useful. It has a lot of different arguments. We're not going to use all of them. Basically, you should manage or edit the ones that we're using right here. Okay, so in this case, the first thing that you should tell the data summary balance is what is the formula that you're going to be using. And what this basically stands for is how many groups you want to divide this in. So in this case, I only want to divide it between the treatment and the control group. So what this is showing me, this formula right here, is that each covariate that I have is just going to be regressed over treatment, and that will give us the average both for the control group, which is just the intercept, and for the treatment group, which would be the intercept plus the beta coefficient of the treatment, right? So we will get both averages. And the main advantage here is that because we're estimating that beta, right, that's going to capture the difference between the treatment and the control group. And we can know whether that difference is statistically significant or not. So that is what this function is doing kind of on the background. We need also to give it as an argument what data I'm going to be using. So in this case, my data set is going to be dval. And we can play around with the title of the data, with how many digits I want my averages to have. So in this case, I just want 2 decimal points. But again, depending on the data that you have, you can adjust this or not. And finally, one thing that you do need to change is this deemed statistic argument. Okay, by default, this table is going to give you the standard error of the difference. And even though that's very helpful, a lot of the times that's difficult to interpret in terms of statistical significance. So we're going to ask this to give us a column with, instead of the standard error, the p-value. Okay, so that is actually a bit more informative to know whether the difference in means is actually statistically significant or not. So let's run this line right here. And this is basically the output that we get. Again, these first 2 columns right here are the mean and the standard deviation for these different characteristics for the control group. And these 2 other columns right here are the mean and the standard deviation for these different characteristics for the treatment group, right? So for instance, in the control group, CVs have on average 3.7 number of jobs, right, listed there, while in the treatment group, it's also 3.7. So basically it's perfectly balanced. And this column right here, the difference in mean, shows you that actual difference, okay? So you would want this difference in means to be pretty small, right? That's something that you would want to see. So this very kind of close to 0, or very small, depending on the units that these covariates are listed as. This P column right here, what it gives you is the statistical significance of this difference. So basically, whether we can reject the null hypothesis that this is different from 0 or not reject it, okay? So again, we want these differences to be very close to 0. We want these p-values to be very close to 1, okay? So we don't want small p-values here. Small p-values will indicate that the difference is actually statistically significant, right? So as you can see here, most p-values are actually quite large. They're very close to 1, so this is great, except for this variable right here, computer skills. So as you can see, this is a p-value of 0.03. This means that at conventional levels, this difference of 0.02 is actually statistically significant between both groups, okay? This difference still is not very large, so I'm not very worried about it. And again, this data set has a lot of covariates. So I think I mentioned that it has like 62 covariates. Just by chance, at least 3 of them are going to be statistically significant at a 5% level, Okay, so if there are like 3 in the whole 62 list of covariates, that is fine. That is totally normal, and it could happen by chance. On the other hand, if 30 of them are statistically significant compared to the whole list of 62, then that probably is an indication that your randomization was not correctly done, and we should be a little wary of the data that we have. Okay, maybe that means that the randomization, something happened, and clearly both groups are very unbalanced. Okay, so we should be a bit more careful. In this case, if it's just 1 out of the how many covariates are there, it is absolutely fine, and this could just happen by random chance. Great. There are other ways to do this, and I list them right here. I'm not going to go into them, but again, give it a run. Here we're using the group by function again. You can test it out and play around with it, but I would say that data summary balance is one of the best ways to do it. And again, it gives you a very neat, clean table. Great. So the first thing that we wanted to do was check for balance. We did that. We see that both groups are well balanced between each other. So that's great. And now we get to analyze. As I mentioned, analyzing an RCT is very simple. Okay, we just want the simple difference in means between the treatment and the control group in this case. So that is what we're going to do. And remember that to get that simple difference in means, all we need to do is run a simple regression of the outcome on the treatment variable. No covariates, nothing else. Okay, remember that because the treatment assignment was actually randomly assigned, it is not correlated to anything else, so we do not have a confounding problem. So this model will actually yield a causal effect, okay, a causal estimate. So let's do this, and we're just going to run a simple linear regression. And again, we wrap it up in summary. The reason I'm using LM robust, and I'm not going to go too much into this, but again, for all purposes right now, it looks exactly the same as a LM function, as the linear model, okay? But basically, it treats our standard errors a little bit different. So it corrects for heteroscedasticity, which is a term that you should not be aware of yet, but we'll get to it in a few more classes. But for now, I'm going to tell you when you need to use LM robust or LM. That is fine, but just for you to be aware of that. Again, output is practically the same, so you should analyze it in the same way. Great, so we run it, and we can see right here that we get a treatment coefficient of minus 0.03, okay? If I wanted to actually interpret that coefficient, I would say that CVs with a black sounding name have, on average, a decrease in callbacks of 3 percentage points compared to white, or CVs with white sounding names, okay? And that is a causal effect, okay? So the effect of having a black sounding name on your CV versus having a white sounding name is of a decline in callbacks of 3 percentage points. Great, and that, of course, if you see the p-value right here, is very statistically significant, okay? And that, again, is a causal effect, and that clearly gives us evidence of racial discrimination, at least in the labor force, for just calling back someone. So what would happen now if we had covariates? So we can do exactly the same, run the same model, but now instead of just including the treatment variable, we can add a different set of covariates. In this case, as we saw in class, the coefficient, the treatment effect, should not change at all, okay? And why is that? Basically because all these covariates that I'm including right here, even though they can affect whether someone gets called back or not, they are not related to the treatment, okay? Remember that the treatment was randomly generated. So basically, all these covariates right here are not confounders, okay? So because they're not confounders, they're really not capturing any of the, or should not be capturing any of the treatment effect between treatment and the callback, okay? So what we would expect to see is a very, very similar point estimate from the simple model. So let's run this and see what happens. So as you can see here, we get that when you increase education, actually, or most of the time, your probability of getting called back actually increases. That's something that we kind of expected, so it's great. And the treatment coefficient, as you can see here, it's still minus 0.03. So very similar to the minus 0.032 that we have right here. So again, this is something that we want to see, and we would expect this. If this coefficient were to change substantially, like for instance, instead of being minus 0.03, now when I include covariates, it shifts and changes to plus 0.05, then that basically means that these covariates that I'm including here are affecting that coefficient, okay? And that is a very, very bad sign for my RCT. It probably means that the randomization was not correctly done, and those groups were not necessarily balanced, okay? So we should be very wary of that, and this is also a very good robustness check, running both the RCT without covariates and then adding those covariates and seeing that the point estimate actually does not change substantially, okay? So hopefully that clears up this a little bit more, and I am happy to talk about this more if you have any questions about it.